The Big Bang, the Big Boom. So, this is our universe. Dun, dun, dun. So, look, guys, we don't know the whole thing, okay? We don't know the whole damn thing. But this is what we got so far, okay? What we got is a big old space-time, okay? And what you see is, this is today, 14 billion years ago, after the Big Boom. You go back in time about 14 billion years ago, and we see the universe become smaller and more dense. Do you see this, guys? You see how the galaxies are so spread apart? But if you go back in time, it's like they're closer together, right? It's weird. It's strange. What this tells us is that there must have been a point in time when the universe was small, like smaller than a grapefruit. All the matter and the dust and debris and all the stuff we know of was clumped together in this one little volume of space and time. And that's how far back we can see. We don't see anything further away. In fact, there's no light for us to see further than that. And there was no light at all for us to see. So our modern understanding of physics breaks down at the Big Bang here, okay? What this thing represents, we don't really know for sure, okay? But there are some ideas, perhaps a quantum fluctuation. These are fluctuations in energy, in vacuum of space. It's weird, it's strange. But perhaps there was a fluctuation or some kind of inflationary event that gave rise to all that matter that was clumped together right there. And then, pa-boom. It's not that it exploded. Don't think of an explosion, okay? You have to think of it as stretching, right? Like me and your mom last night. We were stretching it, okay? We were stretching it. And all the galaxies were like this. Like this. All this stuff and matter, right? There was no galaxies back then. A second after the Big Bang, there were no galaxies. But there was matter in this weird state. And then it clumped together to dark matter. Dark matter you can't see. Light doesn't touch it. Light doesn't interact with it. But it is the machinery that gave rise to the clumps of galaxies we see today. It was what shaped our modern universe. So we'll see here. Let's go forward in time now, and you'll see what I mean here. Say we got the universe, we got the galaxies. Okay. You go back in time, you get the Big Boom. Now, the Big Bang was extremely hot, okay? It was all the stuff, all the matter in the universe was super compressed. And when you compress things, what happens? It gets hotter, right? So there is this weird state of matter called quark-gluon plasma. And the particles we know today didn't exist yet. In fact, it was just quarks and gluons, the building blocks of matter we know today. And then from there, as the universe expanded, it got colder. In fact, all the forces of nature, the weak force, nuclear force, right? All the forces, gravity, all the forces we know of were all clumped together as well into something called a super force. Really strange, okay? But that was the Big Bang. Now, there was this rapid inflation period, and the universe then expanded, and when it expands, it gets colder. The average temperature of the universe got colder, right? And there's this, what causes the expansion consistently was this dark energy. It's this property of space and time that's stretching apart space and time itself, right? Remember, like I said before, that band, that rubber band? It's like stretching a rubber band. So the universe expands, it gets cold, and now these larger molecules and particles are able to form nuclei, the first atomic nuclei, the things that make up your body, right? Atoms. Makes up those atoms are nuclei. protons, neutrons, right? And then electrons. That comes after the universe cooled. In the first 400,000 years of the universe, there was no objects. There were no objects yet. It was just dark. The Dark Ages. Light was not able to reflect off of anything or even pass through this foggy smoke. This weird matter, right? It was just so much stuff. It was like fog, like a foggy day. You can't go past, you can't see what's past it. But then as the universe expanded even more, atoms were able to form. And what this meant now, that fog went away. The fog disappeared. And now light could not only pass through it, but also reflect off of objects. So what we have here is the first 100 million years of the universe, which was dominated by dark matter. Most of the matter in the universe, like 85% of it, is dark. It's not like what we are made of. It's made of really weird stuff. Then, dark matter forms galaxies, stars. These stars are made of those gases that then collapse, right? All that heat and stuff collapses into the center. Because of angular momentum, it pushes things to the center, causes a star to form. Nuclear fusion begins in the core. See, this is what dark matter was doing, right? It was making these galaxies form. It was like the seeding of all these galactic structures around the universe. Really strange. Here's a really sped up version of what was happening. Galaxies are connected via these galactic tubes. They're called galactic filaments. And now we know today that there's like a webbing of galaxies. And they're all connected via these tubes that spin and rotate. And actually, we know that galaxies can get spun into them and spin out. And perhaps that's the origin of galactic spin. We got more stars going supernova, right? Now we got heavy elements. See, because in the early universe, there was no carbon, there was no oxygen, there was nothing that makes up you and me. So where did it come from? Well, it had to come from stars that were kind enough to explode, right? Those big ass stars with all that mass, all that ass. In the very core of those big stars, there was so much pressure, so much heat, that even atoms themselves smashed together. I mean, it was quite rare. But there's just so much stuff at the center of the core that the amount of atomic fusion that occurs is enough to bring light out into space, right? Light shines out. Those atoms smash together and they fuse together into larger elements. So hydrogen can fuse into helium, and helium can fuse into carbon, and carbon can fuse into heavier elements like silicon and nitrogen. And that's the origin of the stuff you're made of. And they're made in these big stars that then build up in their cores for millions of years, and then they explode under their own weight. They're so massive, they can't take it anymore. Once that energy, that pressure going outwards from the center stops igniting, if there's no more fuel for the star to burn, it begins to collapse and explode. But because those big stars in the early universe exploded very frequently, they give rise to solar systems like ours. Because remember, all those elements that were in that star it went out into space and then formed these big gas clouds called nebulae, which then collapse and form new stars. So there's this recycling of stars that happens throughout our universe. In fact, the elements you're made of that were found in our solar system in the early origins of it, some of the stuff in your body comes from multiple different stars that have exploded. Perhaps a carbon atom in your left eye and a carbon atom in your right eye came from different stars that exploded 6-7 billion years ago. But they made their way to here, to our star system, which then formed our sun. And then our sun, in the early stages of our sun's history, it releases a shock wave. A childhood of a star releases a shock wave and pushes material outwards. So all that stuff gets pushed outwards, and because it goes away from the sun, it becomes colder. It's cold out there. But because of this, all that gas and dust and debris was now able to precipitate into larger fragments. Planetesimals, rocks, ice, right? So all that debris that was once dust got cold enough to make larger rocks, which then clumped together due to gravity. In space, there is no air in the way. It's just cold welding. It just welds together in space. It's really weird. But that's what happens in space. Rocks love to clump together, lock into each other. So here we have our early Earth, right? Imagine these little fragments become bigger and bigger and bigger. They get clumpier and clumpier and clumpier. And our early solar system perhaps had maybe 15 planets, 10, 15 planets the size of Earth. Some of them got smashed together, forming larger planets like our Earth. Some of them went into Jupiter or Saturn, got probably engulfed by them. But eventually we were left with the 9 planets we have today. Now, Earth, about 4.5 billion years ago, was very hot. It was molten. It was almost liquid. It was so hot that there was no surface that was solid. It was just a molten ball of molten. In fact, that's the moon. One day, about 4.5 billion years ago, a planet the size of Mars smashed into Earth, and a huge chunk of it went out into space. There it is, you see? There it is. That went back to Earth, and there's the moon right there. The little fragment that's left. That's the moon. That's how the moon formed. And the moon got stuck in its orbit over time and was able to form the moon and the Earth. Now, some of these rocks that are in space have lots of things called carbon and water in them. These are hydrates, carbonaceous chondrites, which contain hydrates in them, which encapsulate water, frozen water. Now, when these rocks bombard the Earth, what happens? They freeze, they vaporize, right? They vaporize in the Earth's atmosphere, producing water vapor. And that was some of the first atmosphere of the planet. Lots of water vapor, lots of methane, lots of CO2. And these things produce the Earth's first atmosphere. And then what happens as the Earth cooled down? Precipitation happens. It starts to rain. You get liquid water on the surface. Oceans form. They become salty as the surface starts to lock in. Right? That's where all the salt comes from in the oceans. It comes from the crust, the continental crusts around the world that have solidified after the first plate tectonic activity. Now, a lot of that water seeped onto the underground of the Earth. And a lot of it went down below. And what happens, you have water underneath, there's the oceans, and lots of activity under the oceans. You have radioactive materials decaying, giving rise to heat. And molecules. You have the first amino acids. Some of these amino acids in the oceans come from space as well. Some of these amino acids are just simple ingredients, right? Look at what they're made of. They're made of hydrogen, ammonia, methane. Very simple molecules that then go into making amino acids. The stuff we're made of, were made in the universe. And over time, these molecules interact in weird ways. These are lipid bilayers. They form due to those amino acids can form certain molecules that certain lipid molecules as well. Same process, but different molecule. They're called lipids. These lipids can form layers because of the different polarities. One side likes water, one side doesn't like water. And when this happens in the oceans, they form a spherical structure called a protocell. This is what the first protocell was made of. But then those amino acids also gave rise to RNA and DNA and all those things, and they start replicating, right? They start doing some funky things. The first life, bacteria. Bacteria gave rise to some of the first oxygen about 3.8 billion years ago. The first living organisms, they gave rise to oxygen in the atmosphere. The oxygen then seeped into the oceans, giving rise to dissolved oxygen, saturating the oceans full of oxygen, allowing more multicellular life to metabolize better and become larger, become fish. This is 708 million years ago. The first animals, right? The first fish, 700 million years ago. 400 million years ago, the first land animals. They walked on land. Why? Not because they just suddenly grew legs one day. But natural selection has a way of forcing or pressuring these animals to, get closer to land. And perhaps these animals perhaps, preyed on some animals on land, or perhaps they mated on land, but they weren't fully on land yet. They were amphibious. But these first amphibians became reptiles over time. They diverged into reptiles, and then mammals actually diverged from the reptiles as well, about 250, 300 million years ago. Then dinosaurs as well arise from the reptiles. Dinosaurs, they become some of the most advanced predators ever known. They dominated for 200 million years on our planet. Dominated. But, as we all know, something bad happened 65 million years ago. Poof. Dust and debris blocked out the atmosphere, blocked out the sun for years. The initial impact vaporized anybody within miles. Vaporized completely. The sound waves were so strong, you would go deaf. You would actually burst from how powerful those sound waves are. The seismic waves that from underground were so strong that anything would just as well crumble because of the activity happening in the Earth's crust. The sun was blocked out for years. Plants died. 75% of all living beings died. Any animal that was over 30, 40, 50 pounds died. It was impossible to survive because you relied on so much food. It was more easier to be a scavenger and scavenge the dead remains of the species that lived before you, and the dead, plants and things, and perhaps the dead fish or fish that remained. But then 60 million years ago, the mammals emerge from the underground. They go, wait a minute, it's nice out here. Let me see what's out here. Okay? They go out into the nature. They start going and living in trees, right? The first mammals 20, 30 million years ago, they start living in trees. Apes, the first apes 15 million years ago. Okay, they start living in trees, eating fruits and vegetables, living in families, chilling out, mating a lot. And then the first humans, 2 million years ago, they walk out of the trees. They leave the trees. They were forced out of the trees in Central Africa because of climatic changes. They were forced to walk through the plains of Africa, migrate into other territories, learning new habitats, learning new water sources, learning how to survive, learning fire. Okay, 2 million years ago, we discovered fire. This propelled our advancements. tools and stones and all these things. And about 20,000 years ago, we pretty much dominated all the continents of the earth. Every continent, even Australia, was full of people. And then 12,000 years ago, the first agriculture begins. The first places and cities and civilizations that you can hunker down in and, have a family and trade. Economies begin about 6,000 years ago. Ships and things like that, right? Economies emerge. Wars emerge. They battle for land. Hey, this is my land. No, this is your land. Let's fight over it. Okay, it's my land now. Okay? The rise and the fall of plenty of empires take place during this time throughout Europe and Asia. And then about 2,000, 3,000 years ago, the first literature, the first written language, enabling humans to finally transfer their knowledge to their children and to their future descendants. This propelled us even further, right? Look at the snowball effect of changes that occur. 1543, the Copernicus revolution. He discovers that the Earth isn't the center, that the sun is. That there's a new way of seeing the world, right? It's not just that we are the center. This changes. Counters lots of religious people, lots of religious leaders at the time. They were confused. They thought he was evil. But then Newton comes out with his laws of gravity. Okay, he discovers things like gravity, light with prisms, and all kinds of amazing things that change the way we see how motion happens in our universe, sparking the Industrial Revolution in the 1700s. In Europe, Northern Europe, it really began there in Northern Europe, where they had the steam engine, things like that, enabled by, basic laws of mechanics and gunpowder, and wars became more advanced, and automobiles in the early 20th century, planes, ships, larger ships, planes, the space age, 1960, the first astronauts, the first people go to space, right? We start reaching outwards into the rest of the universe. 1993, the Hubble telescope, internet comes out, right, connecting us globally as a global economy. The Hubble telescope discovers amazing things out there. 2008, iPhone, social media emerges, right, changing the way we live. 2022, AI, the first open AI where anybody can use it. The common people could use AI. Present day, 2024. With the 14 billion year journey that was. Okay, and we still got lots to go. Lots and lots and lots to go. Did you guys enjoy that? We borrow from a religious perspective for a creator to not exist. The title is it's on my YouTube. This is my video. Yeah, it's amazing, right? Our journey. Knowing the journey absolutely helps us understand more about our place in the universe and appreciate things more. Best teacher I've ever had. Thank you, Emo Barbie. What's my diet as a vegan? Your mom. Any questions about that, guys? Make them easy. Where did life come from? I just fucking explained it. Do I have to do it again? Look, I have a video about that on my channel called Abiogenesis Explained. But essentially, there's a chemical process that happens in the early Earth, lots of chemistry going on, right? You have amino acids turn into peptides. These peptides can turn into polypeptides. They form chains. These chains form sheets of amyloids, which then can metabolize things and produce more amino acids, which then give rise to more amyloids, right? So there's kind of this chemical evolution that happens. And after enough of that chemical evolution, things begin to get more complex. They begin to replicate. They begin to really replicate self, independently, giving rise to really the first living things. Now, that's all life means, right? People have this assumption that life is somehow this special magic process, special magic object. There's nothing about you that makes you special except for the fact that you are the emergent phenomenon of all those chemical processes in your body. So there's no object that makes you alive. You're looking for that one thing that life comes from. It doesn't exist. Life is just a process. It's just a chemical process. So if you see life that way, it changes the way you ask the question. That question, where does life come from, is a very good question, but a very misinformed question. It doesn't come from somewhere. It's a process that things do. It's a process that non-living things do.
Hey, Mike, how's it going?
Good. Remember, guys, this water that you're drinking literally is 4 billion years old. This water comes from space, literally. Those rocks that I was talking about before, those rocks that then filter down through millions of years into this fresh water we know today. Very fascinating. Just remember that every time you drink water.
Oh, yeah.
Yeah, how can I help you?
Yeah, I have a quick question. Obviously, vegan's in my name, so I'm very vegan. But for diet aspect, for health reasons, is there any reason people couldn't go, plant based? Because you hear all the time, like, well, I was vegan, but I stopped, my health got better.
Look, anybody can be healthy as a vegan. And veganism is not a diet, it's an ethical position.
Yeah.
But can everybody be plant based 100%? Probably not. There are probably some people that have certain conditions that require them to use some animal products at least. But for the most part, everybody can be plant based, and evidence shows that plant based diets are healthier by far.
Right, yeah. Yeah, I was just curious on your take on that.
Okay. Thank you. Appreciate it. Who wants to come up and ask a question?
What's up, Mike?
Yeah.
Hey, man, I see you're gonna debate Parker and Dean. When is that?
Wednesday.
All right, man. Is it gonna be in your platform or their platform?
Probably theirs.
Okay, I might stay tuned for that, man. That's gonna be a good debate right there.
Yeah. Thank you.
Yeah, no problem, man. That was it, Mike. That was
What
it.
else? What else you want?
No, that was it. I was just asking when y'all were gonna
Okay.
do the debate.
Go. Okay. Go. Go away. Oh, somebody's coming up. Somebody's coming up.
To accept Jesus
Hello.
Savior.
Our Father, who art in heaven.
You need to repent now before it's too late.
Okay, have a good day.
Good boy, Michael. Good boy.
No Chick-fil-A sauce? Mike, is this a debate live? No, this is a chill live. Where's the questions? I'm waiting for questions, guys. I love the questions part. Come on. Ah, sheesh. You guys are the worst viewers. Where am I going after TikTok? Your mom's house. Switch to natural shampoo. Go away, bro. I don't need your nonsense. Can you talk about how fast the universe is expanding? Well, it depends on where you are. The expansion rate is not consistent throughout the universe. The further away you are from Earth, the faster the universe is expanding away. In fact, the other side of the universe might be expanding 10, 20, 30 times faster than the speed of light. So the universe is expanding faster than light in some regions. But around us, we don't really see that. But in terms of expansion through time, the expansion has been way more rapid in the past and has since slowed down. We noticed it has sped up a little bit, but now we think it's slowing down again. It's really hard to understand the speed of the universe. Do you think we're in for a collapse, like fading universe? We don't know. It's possible. However, there is some recent data from the James Webb that really challenged the notion that the universe will continue to expand forever. We recognize that the universe is actually slowing down a bit in its expansion. So it's strange. We don't know yet. It seems like dark matter, dark energy, isn't what we thought it was. Is the moon rusting? Well, there are certain processes in the moon that allow for rust to form. It's natural. Rust is just iron and oxygen. And where does oxygen come from on the moon? Well, there's water on the moon. Water can form rust on the moon, but it's not very much. There's very little oxygen. There's very little iron rust on the moon. It's not turning into rust. It's not turning blood red. It's just some regions. Okay. What would happen if the universe stopped expanding? Nothing. We wouldn't notice at all. If the universe stopped expanding, we wouldn't really notice at all. In terms of like our movement through the universe, we wouldn't notice. We would notice with telescopes, but we wouldn't notice at all. In fact, if the universe expanded even faster, we wouldn't notice. So it wouldn't really affect us at all in terms of that until billions of years in the future. However, if it stopped expanding, potentially it'll collapse again, trillions and trillions and trillions of years in the future. Potentially. We don't really know, though, because it depends on the configuration of matter in the universe. How could we see the Big Bang if we came out of it? We didn't come out of the Big Bang. The Big Bang happened where you're standing. The Big Bang happened everywhere. It happened where you're sitting. The Big Bang happened at every point in the universe. Every point in the universe is expanding, and that's all the Big Bang means. So it's not like we come out of it like an explosion, like Fast and Furious, like Vin Diesel comes out of the explosion. Like, no. We are part of the universe's expansion, and we are just precipitants of it. What's the chance of it collapsing? We don't know. I don't know for sure. What would happen if the Earth stopped moving for 1 minute? We'd all die. So right now we are moving at 1,000 miles an hour at the equator. It's a bit slower the norther and more south you go, but at the equator it's about 1,000 miles an hour relative to the axis, the actual tilt of the Earth. And because of this, we are grounded on the Earth. We are spinning with it. Everything around you is moving at that rate. I mean, it's all relative. Nothing's really moving that fast. It's just that it's relative to something else in the universe. But the point is that if the Earth were to stop rotating, right, all of our momentum would still be conserved, such that we would all be flung off at 1,000 miles an hour. We'd all be moving at 1,000 miles an hour relative to the stationary Earth. So we'd all pretty much die. Okay, how fast is the galaxy moving? Well, galaxy's moving at, I believe, like 200,000 miles an hour or something, like up to 1,000,000 miles an hour relative to other galaxies. Again, motion's all relative. Nothing is moving with any absolute motion. It doesn't exist in the universe. Motion is relative. It just depends what you're referring to. So there's multiple Big Bangs. Well, there could be other Big Bangs besides ours. Big Bangs seem to occur in the emptiness of space. Space isn't really all that empty. There's actually lots of energy in space that's fluctuating, like a foamy material that fluctuates, and certain fluctuations that are strong enough can bring about this universe. Really amazing. Really amazing. But this is all hypothetical, but possible. What is dark matter and dark energy? Dark matter is matter like ours. It doesn't interact with light. It doesn't reflect light. It doesn't absorb light. It doesn't do anything with light. Light passes through it. We can't see it at all with light. Now, not only that, that's why we call it dark, but also it doesn't interact with itself. So like our matter, right, interacts with itself. Our type of matter, baryonic matter, interacts with other matter. Dark matter doesn't. It's kind of just there. Now, it has an effect on gravity, on space and time. We can see the curvature of space and time it generates. But that's all we can see. We don't see it with light. It doesn't interact with other dark matter. It's just a blob of stuff that's just sitting there and has some kind of effect on space-time. But it seems to be the glue that holds together our galaxy. And it's more prevalent than even baryonic matter. There's more dark matter in the universe than any kind of our matter. Way more of it than us. And dark energy is this weird property of space and time. It seems that space and time, much like gravity, has this attractive force to it, right? If I threw this bottle in the air, it comes down because of gravity. Gravity has this attractive force to it. But in space, the opposite can occur. Not only can space-time facilitate this gravity force, but it also facilitates this anti-gravity force, this repulsive type of gravity that repels things from one another. So instead of me throwing this bottle up in the air and it coming down, I would throw this bottle in the air and it would keep going up and up and up in a faster rate. So, for example, if I were to drop this bottle to the earth, it would come down with an accelerating force. It would accelerating speed, right? 9.8 meters per squared second, squared. However, dark energy is such that if I were to throw this bottle in the air, it would go upwards at an accelerating force of 9.8 meters per second squared. That's kind of what dark energy is. And it's built into space and time such that it pushes it apart. So if any dark energy exists there, it wants to repel from each other, right? It wants to move away with an acceleration. And that's what space and time seems to be like. It seems to have this weird property that exists all around it, and that's why the universe itself is really being repelled. So since the early universe, there is this counteract. There is this counteract from matter. Matter wants to attract things, and dark matter wants to repel things. And in the early universe, there is enough saturation of matter such that the dark energy was masked, such that it would not expand anymore because matter was there. But as matter thins out in the universe, expansion will continue to go on and on. So that's why there are different rates of expansion in the universe, because it depends on how much matter there is, how much saturation of matter you have in a given area or time. Okay. Sorry for the long-winded response. It was a very important thing to talk about. Mike, you better smack Dean and Parker. Is there anything moving faster than the speed of light in relativity? No, nothing moves faster than light. And the reason why is there's no space to travel faster. It's very weird how it works, but everything in the universe is actually moving through space and time at the speed of light. We, you and me, are moving through the universe at the speed of light. It's just that almost all of our motion is in the temporal dimension, the time dimension. We're moving almost all through time. We're moving very little through space, right? I'm not moving through space much, but we are moving through time, okay? So we don't see the time dimension. We see 3 dimensions of space. But from a higher dimensional perspective, there is another dimension, a physical dimension of time. And we just don't see it. We don't have access to it, but it's there. And because of this, there's not enough room for me to move faster than... There's not enough room for photons to travel faster than the speed of light, because all of its motion is in the spatial dimension. It has no more time dimension to move in. So that's the point. Everything in the universe is moving at a constant rate through space and time. It's just that there's this balance between how much space or temporal motion you have. It's very strange, but that's how relativity works. And it's mind-bending. Is there a principle of operation that explains dark energy in the quantum level? Well, if there was a theory that could explain dark energy, it would be quantum field theory or string theory, perhaps. There's all kinds of quantum gravity solutions like loop gravity and all these things, but Yes, there are solutions that allow for gravity and dark matter to arise and dark energy to arise or emerge from quantum stuff. Everything's quantum, really. I mean, that's the trend in science, is that people are recognizing now that, yeah, everything is really quantum. It's just that we have to make sense of gravity. We still don't really know. However, there is the idea of entanglement having a place in space and time itself, perhaps in quantum entanglement. Entanglement is when you have two particles that are entangled together. They share states. They pretty much share the same wave function. And if you have a splitting of these particles, if you break the entanglement and you get space and time emerges from that breaking of entanglement. And we think that if this continues to happen, if entanglement is the natural state of things in the universe, it is so common, and the space-time is so commonly emerging, well, it's possible that quantum entanglement is actually the fabric of the universe itself and responsible for gravity and dark energy. So, again, this is very, very fringe, but it's a possibility. Do you think we'll ever fully grasp the universe? Hell no. And that's good. It's amazing that we're here thinking and pondering about these things. What does it even mean to say fully grasp the universe? I mean, that question doesn't even make sense to me. I mean, how do you know everything? Because every time you think you know it, something else could challenge that. How do you know everything? Maybe knowledge is never ending. Maybe knowledge never stops. Does being vegan mean I can look like Mike? Yes. Can four-dimensional beings go back in time? No, you cannot go back in time. However, there's a couple caveats there. There are lots of loopholes that you can take advantage of. There's time-like curves and wormholes and time dilation, but can you go back in time in terms of flipping the switch of a button and going back to 1900? No, that is probably not possible, because Einstein showed us that all the time already exists. What we call the past, what we call the future, still exists right now. It's all the same. There's no sense of passing time that absolutely exists. Time doesn't pass. It doesn't. It seems like that from our perspective, but it doesn't pass. So because of this, I think that the only possibility of traveling through time is going to be experienced through time dilation, in the sense that if you move faster through space, you're kind of losing time because of that. And you're exchanging time for that. And that's the sense of time travel that you can have. But I don't think that it'll ever be possible for us to press a button and go back to 1900. I think that is nonsense by definition. We can't know space, but we do know scientists tamper with nature. Now, you asked me four-dimensional beings. No, you can't go back in time either if you're a four-dimensional being. But what you can do if you're four-dimensional is see all the time. You can see all the time. You just can't touch it. You can go back into it, but you can see it. Just like a three-dimensional being sees all sides of a two-dimensional being, right? If I look at a square, I see all the sides of a square simultaneously. All the sides of a square are right there in front of me. A four-dimensional being will be able to see all of my sides at one time. A five-dimensional being would be able to see all of the four dimensions, including time, right? So if you're five-dimensional, you'll be able to see all of time. what we call the passing of time. You'd be able to see it right there. Very, very strange. But this is what relativity allows and actually demonstrates. Much like Interstellar. All right, a couple questions, then I gotta go.
Hello? Yo, what's up, Mike? Bro, so I was debating one of my friends, and I don't know, like, are you a physicalist?
Yeah.
Yeah, so I was arguing reductive physicalism, and he asked me the question, well, how does it feel to be human? And I said something like, well, that's just like a thought in your brain that results from like electrochemistry, right? But I don't feel like that was a sufficient enough answer. Like, what would you have said there?
Yeah, well, what does it feel like to be human? That is, you're on the right track. It is electrochemical, but it's not just one reaction, right? It's the sum total of all the processes in our body happening simultaneously. It's the emergent property of all the bioelectricity in our body, the neurons in my brain, the nerve endings in my body, right? The electrons moving through my body. That is what experience is. Experience is synonymous with this sum total of all of our bioelectricity. I mean, we are electrical beings. So we experience through bioelectricity. That's what I would say. Now, this is just a, physicalist's perspective. This is not necessarily the case, but it's just that's a better answer. But yeah, it's
Okay, yeah, I got you. Another question. So you define the mind as you think the mind is an emergent property of the brain, right?
yeah.
What do you define the mind as?
What the brain does, the emergent phenomenon of the brain's activities, thought processes.
So like qualia and stuff like that.
Yeah, look, qualia I think it's nonsense. I think that we're confused when we ask the question, what does it feel like to experience redness? That question, I think, is malformed. I think it's the answer. The real question should be, what is experience? And to me, what is experience is this electrical experience, this electrical phenomenon that we are emergent of. That's what I think it is. Like for example, me and you talking right now. Right? This is that electrical process that we are literally speaking through electrical chemical processes. So that's what I would say that our experience is, and qualia is just a fancy term for that.
Okay, I got you. Yeah, sorry. That was the only questions I really had. Yeah, I know. I usually come up and troll you a lot, but I was trying to. Yeah, but I'm gonna head on now. Peace.
Thank you. Can consciousness exist without a brain? I don't think so. And if it could, I mean, then you would have to bite the bullet and say that rocks can be conscious, right? If you're a panpsychist and you think that everything's conscious, or that consciousness comes from outside of the brain or outside of physical stuff, you kind of have to agree that rocks could be conscious, that this water bottle could be conscious. And I think that's a ridiculous thing to say. I think that consciousness is purely physical. I don't even see it any other way. I don't see how it could be any other way to me. I mean, I've never seen anybody without a brain who is conscious. To me, I've just never seen it. Is the universe infinite? Maybe. We don't know. Are pet animals humane? Well, I think if you're going to have a pet, it's okay as long as you recognize that it's not property, it is just a friend. And it's not there for you to breed or exploit. It's there to be a pal and a friend. and rescuing animals is great, but I think breeding animals for the sake of breeding them, for the sake of buying or selling them, I think that is absolutely wrong for many reasons. Would I ever want to do that to a human? Every time I ask myself, would I do this to an animal? I ask myself, would I do it to a human being? And if the answer is no, then I wouldn't. That's consistency. That's really what veganism means. It's about being consistent in how you respond to animal welfare and animal rights. I respect that. The thing that bothers me the most is when people say, oh, I like vegans, or I have nothing against veganism, but I think that's just disingenuous. I think that's just an excuse. It's a cop-out to sound nice, but you're really not. You're really trying to find an excuse to do something terrible. Yeah. Thoughts on the TikTok ban? What am I going to do about it? Picket signs, stop the ban. Stop the ban. It's not going to work. Is the Higgs field related to dark matter, and how does it assign mass? Probably not, though. The Higgs field seems to be very weak when it comes to many different particles. It seems to really only be relevant to certain electrons and certain particles, not to every particle in the universe. There's something more fundamental that we just don't quite understand, that you can probably derive all particles from, but we still don't really know. That seems to be string theory. If I were to bet, I would say string theory has it 80% correct. There's a few mistakes with it, but I think that if I were to guess today, string theory has it right to a good degree. It explains a heck of a lot. What do we mean by force? Good question. We don't. Very good question. I don't really know the answer to that. Plus, I'm tired. So, will AI make humanity go extinct? Well, yes and no. It will not one day. People think it'll become like Terminators, and then one day it'll just wipe us out. No, that's not gonna happen. AI is, first of all, we're very far away from that happening. Just so you guys know, the most advanced AI today is as smart as a lawyer. Okay, we're pretty far away from being taken over, but I will say that we as humans, as biological beings, our value will diminish over time. We will realize one day that our value is just not comparable to AI anymore. We'll recognize that, damn, AI has more value than I could bring to the table. It's discovering more things. It's learning new things more than I could ever learn. It's way more efficient. It's replicating way more efficiently than I am, right? It's just a way more advanced thing. And it's not that we'll just burn out one day. I think that we will slowly die, just like every other species did. Every species went through this. We're no different. Look, that's how evolution happens. You're supposed to die for the new ones to reign and for them to carry on. We're not the last species to ever exist. We're not the last living things to exist, and that's exciting, right? We should be excited to be living in this time, because the next transition is way more exciting than any other. what benefit does life have? Does nature have to keep life reproducing? Nature doesn't care about life. Okay, that's why we're barely surviving today. Nature doesn't give a shit about us. Okay. The only thing that cares about life is us. So you're damn right we're gonna continue trying to survive. That's just what we do. Okay, that's why we're here for 4 billion years. Okay, we're just fucking and chilling and experiencing as much as we can before we die. And why not, right? I think we should embrace life and not ask ourselves, what does nature care about? Nature isn't a person, it's not a sentient being. We don't actually know if AI can truly be sentient in the way we are. It may be able to emulate input. AI is not sentient right now. It is not sentient. It's not conscious. But, however, it's on the verge of that. It's trending that way. But again, there has to be a specific, I think, there has to be a specific phenomenon happening for there to be any consciousness. Performing simple logic, a calculator can do that, right? That's really what AI is today. Right now, it's at the stages of like very simple logic. But I don't know. It's hard to say when exactly it will become conscious, but it will probably for sure. But it won't be the way we are conscious. Nothing ever will be the way we're conscious. We're biologically conscious. AI will be mechanically conscious or digitally conscious. Very weird thought, but I think that if there is a way for our kind of consciousness to emerge from atoms, I don't see why it's impossible for other types of conscious structures to evolve from different types of matter and configurations of matter. It's just like the question is, what kind of consciousness would it be? And I think we'll realize as we move on that there are different types of consciousness. There's different levels, but also different types of consciousness. I think that's going to be exciting to learn about. Was there different species of humans walking at the same time? Yes, absolutely. About 50 to 100,000 years ago, there were several human species living at the same time. A lot of them lived in the islands of Southeast Asia. A lot of them lived in Australia, the southeast side of Asia, Northern Asia, Europe. Many human species. Now, the reason why is because we all diverged about 2 million years ago, or 1 million years ago. We diverged out of Africa. And a lot of them went their own ways, evolved their own separate ways, isolated, and then merged again. There were many times this happened. Many times that many species merged together and met each other again. Because that's what we are. Humans are notoriously wanderers. We're explorers. We're going to explore. We're going to walk around. That's what we do best. Would they be able to have a self-awareness like us? Yes, I think so. However, we do not have the capacity to understand that type of consciousness. We don't. It's just not fathomable to us. But I think that in their own way, they will. Look, if it can happen to us, it can happen to them. Okay? I don't doubt it. There's nothing special about our type of matter. Is there any way to go faster than light? No. No. However, there's a loophole. The speed of light limit only applies to things within space and time, not the space and time itself. So if you were to perhaps manipulate space and time, you might be able to travel faster than the speed of light. But you have to have lots of energy to do so. It's very, very, very energy intensive to do so. It takes a lot of damn energy to move space consistently. It takes a lot of energy. Einstein-Rosen bridge requires more energy than the universe has in it. Really? Wormholes require that much energy? I thought that only meant like moving mass faster than light, or towards the speed of light. I thought that's what it meant. But I thought wormholes are pretty much capable of being produced, hypothetically. What do you call that kind of propulsion that warps space and time? I forgot what it's called. It starts with an H, I think. I forgot whoever discovered it, but whatever. Intelligent species before the dinosaurs existed. Possible, maybe long before. No. No, not at all. There is no evidence of any intelligent species before the dinosaurs. Before the dinosaurs, there were very primitive amphibians and reptiles that were not very bright. The smartest dinosaur was pretty much as smart as a modern day bird. They were not very smart. Yeah. Now, were they smarter than we think they were? Typically, yes. They weren't, incapable of logic or incapable of anything. But they were just not intelligent in any remote degree to us. What about raptors? They were not very smart. They were good predators, but not very smart. But look, guys, there's no reason for smartness to emerge. There's no reason for intelligence to emerge. Why would you need intelligence if you have big freaking teeth and you got a big freaking jaw? You can eat up anybody you want, right? You don't need to be smart when you're a good predator. So, or if you eat trees all day long, you got to be smart. Intelligence is very peculiar to a specific population, because intelligence only needs to arise if you're constantly battling or combating new environments or new data, right? The only reason why you would need a bigger brain is if there's new data coming in that you need to evaluate. No other animal really has that. No other animal was ever pressured to experience that like we were, okay? Because the other animals, if they did that, they would get eaten up. But because of our specific past, we lived in the trees of Africa. We were hidden from predators, and we were fairly smart back then. But when we left the trees and we walked on foot, that's when we really became human. We were exposed. We were forced to learn new habitats, new environments. That's what made us human. And there were a myriad of different reasons as well, but the main reason why is because we explored. That's what we are. That's what makes us human in the first place, right? That's in our nature. What does a baby do? They go gaga goo goo. What is this? They want to see what's in there, right? It's just in our nature to touch things and tap things and break things and dig holes and walk around and explore. It's just who we are, and that's what no other animal really has been pressured to do. Does our brain get bigger every generation? Not anymore. It used to. Now it's going whoop, whoop, whoop. It's becoming smoother every generation. But yes, our brains typically are. Look, Neanderthals had larger brains than we did. We don't have the. We don't have the biggest brains. We do not have the biggest brains. We have the most folding. We have the most tightest connections in our neural synapses. We have a particular type of brain. It's not the size of it that matters. Just remember that. Size doesn't matter. Guys, we're not going to leave. TikTok's not going anywhere, guys. We're not going anywhere anytime soon. They have an entire year to figure this shit out, okay? They're going to figure something out. Don't worry about the TikTok bit. I'm not worried about it one bit. I used to be, but now it's like, fuck it, whatever, who cares? Let it go. Let it go, boys. Let it go. It's going to be aight. Do you think we'll be a type 2 civilization? Probably, but not us. AI. Guys, we humans are very selfish. We're very violent. We're very emotional. We don't have what it takes to be a type 2. Okay, maybe a type 1, but not a type 2. Type 2 is going to be reserved for AI. We don't have the capacity to do it. And that's okay. Because we are forever known as the first species that gave rise to these amazing things. We will be known forever as, like, you know, the first generation of people that invented these things. The first pioneers. But yeah, they'll look back on us in about 1 million years from now. We'll have a human in the zoo. And they go, wow, look at this human. They went to space for the first time. And they'll laugh. All the kids will laugh. They went to space. They landed on the moon. They thought it was amazing. The moon? They couldn't figure out quantum gravity. They couldn't figure out quantum gravity. We'll be the laughing stock, but we'll be the ones who were known as the first people who did this, who ignited the flame. Yeah, so embrace your life as a human. It's amazing to be a human. It really is. It's freaking amazing. Okay? It is amazing. I don't take a second for granted every day. Not only is it amazing to be a human, it's amazing to be alive. Part of this time. Part of this world. This time period in our history. We're making history, literally. We are making lots of history. And it's exciting to be part of.